heard you talk about accelerated spatial approximation for time described as SPDE.
So I'd like to start by thanking Professor Kim and all the organizers for organizing such a great conference and allowing me to come and give a talk. From the title alone, I guess you know that I'm a student of Ishtvan at Edinburgh, and if you've been following his lectures, I think things should seem very familiar. Currently Ishtvan's talking about accelerating the convergence for these schemes, right? He's considering just a finite difference scheme in space, right? So this is sort of the next natural question, right? Could we do as well for schemes that are discretized in space and time, right? Just with respect to the spatial approximation. Okay. If I'm speaking too fast, please let me know, because sometimes I have it of doing that. It might be hard to understand. Okay, so to start with some orientation, we're going to consider here spacetime, what I call spacetime finite difference schemes, for second order linear SPDE of parabolic type, right? So the same equations that Ishtvan is considering, right? These are the equations arising in nonlinear filtering theory. So we're going to consider finite difference schemes on uniform grids in space and time, and we're going to look at the acceleration with respect to the spatial approximation. Okay, so we know rate of convergence for these sorts of equations. Even in the nonlinear case, Professor Junge and Annie Millet have written some good papers on the subject. Okay. And as I said, our goal will be to give sufficient conditions for accelerating the convergence with respect to the spatial approximations for these spacetime schemes. Okay. Okay. So this is, as I said at the start, right, the next little baby step in the program that Krylov and Professor Junge have initiated. But it's still, I think, a long ways away from actually being able to be implemented, because we do much of the same that Ishtvan does, so we assume always that the systems of equations we get are exactly solvable, so there's still some work to be done before we could actually implement these sorts of things, right? Okay. So I mentioned that in general, right, we know that we can't accelerate the convergence in time as well, because of the way that the time arises in our equations, the randomness arises in time in our equations. The plan is I'll first explain a little bit the idea of Richardson extrapolation. So I understand Ishtvan did this on Friday, but maybe if the beer party was a bit much for you, you didn't make. So for some, maybe it will be new, and if not, it's just what's going to happen. Okay, and then second, I'll just review the equations and the schemes and the assumptions, and these should all seem very familiar and natural because of the same as Ishtvan's. And then I'll just explain the main results, and I'll give some idea of the proof, and in particular where the differences in the work that Ishtvan's talking about now. Okay, so for Richardson extrapolation, right, we have to imagine, right, that we're given some continuous problem, right, and we'll call the solution U, okay, and we also assume that we're given some numerical algorithm, right, for discretizing, okay, this continuous process with a mesh size H, right. We're going to call, for now, the solution to this resulting discretization problem as WH, right? And the idea of Richardson extrapolation, right, is then Richardson observed that for a particular continuous problem that he was dealing with, right, when he applied centered differences, he got errors, right, the difference between the discretization process and the true solution to the continuous problem U, right, resulted in expansions, asymptotic expansions in the size, mesh size h, right, the discretization parameter h, okay, where the W at 0, right, in some sense the limiting process, right, so it's the continuous U, right, and all of these UI functions that are in the expansion are independent of H. Further, Richardson noticed, right, that by taking appropriate weighted averages of the solution to the discretization process at different mesh sizes, right, one could eliminate certain lower order terms in the expansion. Okay, so for example, we can eliminate this h squared term appearing in the expansion by combining approximations obtained at two different mesh sizes by taking this particular weighted average. Right, so maybe we do that, right? So for example, if we take as h naught this h, and as h1 this 2h for the centered difference scheme that Richardson was considering, we notice, right, that the first term here, this h1 squared wh naught, right, looks like this for our expansion, right? And if we just expand out the second term, right, so that we plug in now the h naught, wh1, okay, and we just subtract the two of these, right, we wind up with the new average, right, the weighted average that we want, where now the U1 term is going to disappear, right? So essentially we're gaining, we're extrapolating and gaining a slightly higher order of convergence, okay? And there are many methods, right, for accelerating the rate of convergence for all sorts of finite difference schemes and all sorts of finite element schemes. And I just want to mention that for the Richardson extrapolation technique, right, we're doing something that's very non-intrusive, right? So for some, to accelerate the convergence of like certain finite element methods, people use adaptive grid mesh sizes and things, right? But these actually require you to change the discretization process, right? Here, we're not changing the discretization process, right? We're not essentially changing the numerical algorithm that we're using to approximate. We're just doing it more than once at different mesh sizes, taking weighted averages and getting the higher convergence. So I think that's what Ishtvan explained on Friday. Sorry for that if you're following closely. Now that we have some idea of Richardson and extrapolation, I just want to remind you of our continuous problem, right, which in particular is these second order linear SPDEs. Right? So given the usual thing, right, so we have some W rho for simplicity. We're going to take here just a finite number of the FT adapted Wiener processes. Okay, we're going to consider the following equation. So we consider the Cauchy problem for this equation, which should now, be burned in your memory. Where here the L is a second order operator. Okay, I've used a slightly different form than Ishtvan, but it may be just a little bit easier. So this is why. Okay, and M rho is a first order operator. So L second order, M first order, and here we use, of course, the summation convention with respect to the alpha and beta. Okay. And I forgot to mention, right? So we're considering this equation, of course, on 0t cross RD, right, the whole space, and we have the initial condition U naught. Okay. So I hope that makes sense. Okay, so first we'd like to discretize in time. Okay. So for some fixed tau in 0, 1. Okay, we're going to define the time grid t tau, which is discretizing the time interval at time interval 0t with respect to the mesh size tau. Okay, and everywhere you've noticed I've been writing u of ti. This is because I very much want to be able to write u sub I for the points of the time grid and not have any confusion. Okay, so in particular I will use for the increments of the Wiener process, right, when we write down the time discretization, the time scheme, Xi. Okay. Does that make sense? Okay, so then together with our SPDE, right, we consider the following time scheme, right, for each fixed tau. Okay, so this is just an implicit Euler scheme in time. I hope this is familiar, right? So, right, we have the u tau I is equal to the u tau I minus 1, and then we evaluate the L, right? So this is a continuous problem still in x, right? We're just discretizing in time right now. So here I've written the u tau, right? So we know it depends on tau, right? This is sort of important. Okay, with the same initial condition, and yes, so right, this is our continuous problem in x. So in relation to the Richardson extrapolation, right, I said we needed some continuous, some problem that was continuous, right, so that we'll have an exact solution to, right? So thinking about that, right, this is our continuous problem, right, with x. Okay. Okay. So then we want to discretize in space, right? So we define the space grid GH. So here we have some non-zero real number h, okay, and a finite subset lambda of our D, okay, and we define the following space grid. So here is a little complication. I didn't realize Ishtvan was just going to be using a particular set of lambdas, so he just chose the natural directions that you would want to, so it doesn't have to be that way, right? But if you want, you can just consider this, so the EI for the directions, yeah. Okay, and further we define the following spatial differences, right? So we have the same, the delta h lambda of phi, okay, it's the same definition that Ishtvan gave, right, where we have, when we take our direction lambda to be 0, we take it to be the identity, and otherwise this definition, right? And so we notice that h can be positive or negative, right? So this defines both the normal forwards differences and backwards differences, right? So that's useful. Yeah, go for it. Yeah, please.
May I ask you how the GH forms work? I can't see what this is.
Okay, so this we're taking lambda, right? This L, lambda, right? A finite subset of RD containing the origin. Okay, you can choose a particular one if you want, right? So we could just take the EI dot 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 ED, right? So this is what Ishtvan was doing, right? You're taking a particular basis, right? So maybe we do that. That makes life simpler.
I missed the point.
Yeah.
Is the GH d-dimensional, so there are multiplication by unit vectors?
So yes, these lambda 1, right, you can choose to be the unit vectors. Yes?
Okay, but so let me see. So lambda d-dimensional.
Yes. Yes.
What's the purpose of minus of the minus?
So we want the h to be positive and negative, right?
Well, you can take
But then we want So you're asking why do we take the lambda union minus lambda? Yes.
If you want to have symmetric difference.
Yes, so exactly this. Thank you. So if we want to take not just the first order differences, but we want maybe the symmetric, the centered differences, right? We would then need both. We need lambda union.
His point is that you can say finite, but lambda to be lambda union what is lambda. We call this lambda. I think this is it.
Yeah. Okay. Yes. Okay. But, so apologies if this is causing great confusion. I probably should have just chosen something simple. Chosen unit vectors. Okay. Well, if you'll forgive me, I'll move on and we consider the following space-time difference scheme. So for each fixed tau, right, we now replace our continuous differential operators L and M by difference operators, here LH and MH, where the L is the second order difference operator and the M is the first order difference operator. And so I should say with initial condition U naught. Okay, so we're taking the same initial condition. Okay, so we assume the following, right? So we're going to want a consistency condition, right, which says that, so I should mention here, I've written here a different A and a different B. This is fine, right? We could take, a discretization of our A, right? That's all that is. Okay. So we'll need some consistency condition, which I'll explain in a moment, right? A strong parabolicity condition. We'll need suitable regularity of our initial condition and our free terms, and we'll need suitable regularity of our coefficients A and B for both the SPDE and the scheme. Okay, so the consistency assumption is as follows. It looks quite horrible, but all it's saying is that our different scheme, right, is in some sense a faithful approximation of our SPDE, right? So that when we discretize, the error, right, is going to be minimal, right, in some sense. Okay. And here we have a strong parabolicity condition, right? So for some kappa bigger than 0, this is familiar, I think, from everything we've been talking about. Okay, and we have some regularity on our initial condition and free terms, and some regularity on the coefficients, right? So importantly, we assume that the A's are m times continuously differentiable in x, right? And the B's are m plus 1 times continuously differentiable in x and bounded by some constant k. So now I'll explain the main results and give you some idea of the proof. I can finish, right? So thinking back to the Richardson extrapolation, right, we need some asymptotic expansion, right, in the mesh size h, right, where this first term, this u tau, right, is the solution to our time scheme, right, where the v tau j I've written here are independent of h, and where we have some control over the r tau h, okay, namely, right, this, so we assume something about the supremum over the time grid and the space grid, okay, and we, okay. So we then have the following, right? So if the assumptions hold with m bigger than k plus 1 plus d over 2 for some positive k, then the error does admit such an asymptotic expansion in the mesh size h. Okay, and the B, so the bound on the error term holds with a constant n that's independent of tau and h. So these were exactly the situation that we wanted to be in, to be able to find the correct mixtures, so the correct weighted averages, and accelerate. Right? So.
Could you go back to the previous page to what A had?
Yeah, sorry. The A was just the asymptotic expansion, and the B was just the bound on the R. I tried to fit them all on one page, but it was too big, I'm afraid. So is that okay? That's right. So very similar, right? So what Ishtvan was saying, except here we're also discretizing in time, right? So we're accelerating the approximation with respect to the spatial discretization. Really, that's just the short of it, right? What Ishtvan's doing, you can also do if you discretize the equations in time. So I'll explain what we need for this just after giving the next result, which is namely that we want to take appropriate mixtures of the space-time discretization at different mesh sizes, right, and combine them to get the higher order of convergence, right, arbitrarily higher order of convergence. So if we take this V bar tau h, which is the sum over the, there we go, the sum over the Bj from 0 to k, the V tau 2 minus jh, right, where the V tau 2 minus jh is the space-time scheme solved now with just a different mesh size, and the same initial condition, right, U naught, and the betas are given by this vector, B naught through Bk, where it's 1, 0, 0, 0 times the V inverse, where V inverse is the inverse of the Vandermonde matrix with the particular entries, and I'm told that Ishtvan covered this in detail on Friday, so I won't make you suffer twice. These calculations can be very painful, right? But you do have to check. Is it clear what the Vandermonde matrix is? And right, it's the matrix with the rows are these geometric progressions. Yeah. Okay. So these are the appropriate mixtures to take, right? And if we take them, right, we have the following: that under the assumptions, right, of the expansion theorem, right, we have the following, right? So if we look at not the space-time scheme, but these mixtures, right, the special weighted averages, right, of the space-time, the solutions at different mesh sizes, we have that we get higher, some arbitrarily high order of convergence, where this k squared m was the function that I described before that was relying on the initial condition and the free terms f and g. And n, importantly here, right, is a constant that's independent of tau and h. Okay, and I guess Ishtvan will explain the proof, and this part is almost exactly the same, right? So we have here the mixtures, right? So we look at what exactly the expansion says about the mixtures, yeah? The same way we did for the Richardson extrapolation that I talked about at the beginning. And since the sum of the beta j's is 1, and the sum from j equals 0 to k of the beta j divided by the 2 to the minus ij is 0, right? We have the following. That's these intermediate terms have the coefficient 0 in front of them, as it did for the u1 term, if you remember at the beginning of the talk, right? And we get the higher order convergence from the bound, right, that we find on the R tau h from the expansion theorem. Okay. Now, how is this different from the proof that Ishtvan's showing you, right? Well, to prove the first expansion result, right, you'll remember that Ishtvan is using estimates, right, for the solutions to these equations in the appropriate Soleil spaces. Yes. Well, so he has this Ito's formula for the square of the norm, but in this instance we don't have that, right, because we're not discretizing in time. However, we do have everyone's favorite equality. A squared is minus b squared, right, is equal to 2a times the quantity a minus b minus the a minus b quantity squared. So we can use the recursion, right, the relation that we had for our implicit time scheme, right, substituting here the a to be the vi and the b to be the vi minus 1, and that's the main difference, I guess, in the proof, right? And then, of course, we have to use slightly different tools, right, to get these estimates, right? So we need to always worry about the displacement of the arguments, right, that we get when we discretize in time, right? So, and as well, we need to use, like where Ishtvan used Gronwall lemma, we need some discrete version of Gronwall lemma, but nothing terribly complicated. Okay. Right, and then we do much the same as Ishtvan is talking about today, so I'm glad I haven't written down in painful detail, right? So if you were falling asleep towards the end of Ishtvan's talk, right, so we need to define some operators, differential operators, LP and NP, by formally taking some pth derivatives in H at 0 of our LH and MH, okay? And then we consider a system of time discretized equations as follows, okay? Where here, right, so this is a system of time discretized equations. Yes, where here we have the free, this new free term L, which is acting on, this is this pth derivative in H of L on all of the previous, right? So notice that it's this free term is only relying on the terms earlier in the. So here, right, for the V1, right, the free term is only relying on the V0 term. Yeah? So the L1 V0. Yeah? And we then have to obtain, right, so results concerning the existence and uniqueness of the solutions to the system and the appropriate estimates. Okay. And then we consider an auxiliary equation, the R tau H, okay, which we get by taking the V tau H minus the U tau H. So here I wrote slightly script V, right, because we're thinking of these as the big L2 valued solutions, as Ishtvan was, yes. Okay. And we show that such an R tau H satisfies this relation, which I call the R equation, with initial condition R tau H 0, where the F and the G are respectively, and I just say, rather than writing it out, because you've seen Ishtvan write it out, right? Certain combinations of the differences between the LH and the L script LJ, right, and the MH and the M script MJ, which are operators acting on certain solutions of the time discretized scheme, right? As a system of time discretized equations. Okay, and right. In particular, right, we know how the F and the G depend on the H, right? So we can use the estimates that we obtain for the space-time difference scheme, right, to give us an estimate on this equation, okay, this R tau H, okay? And then once we do that, right, these were all the L2 valued solutions, so then we have to do the business of showing that we can take the Soleil of embeddings, but we can, because that was our assumption on the M being bigger than the D over 2, that was the important term there, yeah? And show that the restriction of the solutions, the big L2 valued solutions to these equations coincide with the little L2 valued solutions, which are the sort of natural solutions that you would expect to a space-time scheme, that you wouldn't expect this. Okay, so that was it. If there's any questions, I can try and answer them.
First, let's thank the speaker. Let's thank